Okay, so you have a problem. There's this. Your path travel, Justin, looks something like this, right? Where's theta? It's right here, correct? And what's going on? Let's just label these. We'll point this H, P, and R. While traveling up from H to P, what are you on from H to P?
Sand.
On sand. P to R on pavement, yep. And what's the difference in travel time? Or when you're on sand, how fast are you moving? Okay, can you say when you're on sand, what is it? 100 feet per minute. And P to R, you're moving at what? 300 feet per minute. Exactly. Okay. So what's just the first part of the question ask you? First part of the question asks you, just so I can read it out loud here, it says, calculate the time t if you walk 1,500 feet along the paved path and 500 feet along the sand. So for part A here, that time is going to equal what? How far do you go on 500 feet on sand? Divided by what? 100 plus 1,500 divided by 300. You end up with 5 plus 10 minutes. Does it give any initial distances? Oh, it says it gives you a distance, doesn't it? And we'll call that n. It gave you the n to r. What's that distance? 1,500 feet. So in this case, going 500 feet. Oh, and then it gives you another distance, right? H to n is? H to n is, so in this case, what's theta? In this case, what is theta? In this first case? 90 degrees, yes. If you move that point all the way over, what does theta become? 90 degrees, right. So in this case, theta is 90 degrees. So when theta is 90 degrees, it takes how long? 10 minutes. When theta is 90 degrees, 10 minutes. Okay, so part B asks you, calculate the time t if you walk in the sand directly towards the ocean for 500 feet, then turn left. Calculate the time t if you walk in the sand directly towards the ocean for 500 feet, then turn left and walk, and then walk along the beach for 500 feet, 1,500 feet to the house. So essentially, your entire trip is being spent on what? Sand. So sand for how long? Sand for 2,000 feet, right? You're going up and over like that. So sand for 2,000 feet equals 2,000 divided by
100
equals 20 minutes. Now you went out straight to the ocean and then meandered along the sand. Are we good so far?
Yeah.
C. Express the time t to get from the parking lot to the beach house as a function of the angle theta. So here's the big one, right?
Yeah.
Once you get this, you can do all the other ones, but you need this one first, right? So if that's theta, to find how long it takes, what do you first need to find? Distance. You need to find two distances. You need what? What's the first distance you need, or which one of them?
PR or PS.
You need
PR.
the distance from H to P, and you need the distance from P to R. Correct. Exactly right. Exactly. Okay, so which one do you want to find first? How do you do it? No one in the entire class, even the 5 people that said they understood how to do this, has a hint for me. What should I do, Victor?
PR is like 1,500 minus the amount that you didn't walk.
For NP, that's correct. So that's a very good rep. You know that PR is equal to 1,500 minus what in terms of this diagram? No, well, it's just in terms of this diagram right here. NP, yes, that's correct. We could call it, actually, let's call it NP. That is absolutely correct. So in terms of this diagram, that is true. So if we find NP, can we find... Yeah. So what else can we say now? What other relationship could we come up with?
Which NP equals X.
Yeah, so how about tangent of theta is equal to what? Or do you want to use tangent?
Yeah.
Yeah. What is tangent of theta going to be? Yeah. What is HN, though? We know, okay, HN over what?
Over
NP, that's correct.
Which
But what is HN? 500 over what?
X.
NP. Stop using X. Just use NP. Right. So what does NP equal? 500 what? Yeah, 500 over what? Sorry.
Over tangent theta.
Tangent theta. So now what can we do with this new knowledge right here? Plug it in right there. If we plug it in right there, what do we end up with? PR is equal to what? 1,500 minus 500 what? Tangent theta. There it is. What's the only variable in that equation?
Theta.
The only variable in that equation is theta. So that this right here is the distance on what?
On page. On PR.
Distance on pavement. Yes, that is correct. So now we have PR. We know PR. How are we going to go about finding HP? Using sine, exactly. So sine of theta is equal to 500 over what? HP, exactly. So what does HP equal? Over sine theta. So that right there is the distance on what? So if you have the two distances, what's the total time going to be?
Divided by the speed.
Yeah, so let's do pavement, exactly. So pavement's 15, I'll write it first for you. 1500 minus 500 over tan theta over what?
300.
This is on pavement, so it's over 300. Plus 500 over sine theta over what? There it is, right, exactly. So this is, so t theta, time in terms of theta, equals this thing right there. Time in terms of theta is equal to that thing right there. Cool? Nice. Could we clean that up a little bit? Yeah, you can clean it up a bunch. So that's going to be equal to 5 minus 5 over 3 tan theta, right? Plus 5 over sine theta. That's equal to 5 times 1 minus 1 over 3 tan theta plus 1 over sine theta, right? Is that correct? Right? I just pulled out a 5 from everything. I factored out a 5. We good? We can rewrite it a little better. I mean, we have to type it into our calculator like that, but that's 1/3 of what? What's 1 over tangent? Cotangent. Thank you. Plus what? 1 over sine is what?
So
Cosecant theta. Yep. This would be the nice way to write it, but if you have to plug it into your calculator, which you have to do later, which one do you have to plug in? You have to plug in this one, yeah, exactly. The upper one. Okay, so that's the hard part. So D, now it says what? For part D, what does it ask you to do?
calculate the time if you walk directly from the parking lot to the house.
Directly from the parking lot to the house. So directly from the parking lot to the house is going to be this distance right there, right? You could just use the Pythagorean theorem. Absolutely. You could, but what they wanted you to do is plug in theta into here. Let's do it both ways to see to verify if this formula works, right? So this triangle, what do you have? It's 500 by 1,500. So if you're going to do this, they're on sand the entire time, right? You're on sand for this entire hypotenuse. So what's that distance going to be? D is going to be 500 squared plus 1,500 squared, the square root of that. So time is going to be, will be this over what? Over what? No. Oh, 100, yeah, sorry, that is the rate. I'm sorry, yes, exactly. So if you do this out on your calculator, 500 squared plus 1,500 squared, right? Second square root, second answer, and divide it by. So the direct path is 15.81 minutes. We should get the same answer if we plug in the right theta value into the equation we determined, right? So we have to figure out what, in order to plug it in, we need to figure out what theta is. Well, we know tangent, yeah, it gives you that hint. Tangent theta is equal to what? 1500. So so what does theta equal? Tan inverse of 1/3. So if you do tan inverse second, tan inverse of 1 divided by 3, you end up with that, correct?
Yeah.
Now the trick is, let's store this. Let's store this as alpha A, so we don't have to type it out and we're more accurate. What we have to do now is type the big nasty equation that we got right. That's not that nasty. This one right here into our calculator. We plug this into our calculator, and when we graphed it, we ended up with a graph that does go down and then does go up again. Exactly. Okay, so this thing is at, so we're trying to evaluate this at tangent of, we want to do it at this angle value, right? At A. How do you evaluate the function? Do you remember how to do that? If I want to evaluate exactly at A?
Plug it in as a second function.
Yeah, there's a well, you could and do intersection, absolutely, but there's something built into this. That's what I used to do all the time in high school, and then I learned about all these functions that it does automatically. I did all these great programs, like things bouncing around the screen in the longest way possible because I didn't know about functions that were already there. But look, in second calc, look what's there. Look at the first one, value. What value did we save it as? As A. So we just do value A. So what did we get for our answer there?
15.81.
Is that exactly what we're supposed to get?
Yeah.
That's exactly what we're supposed to get. But look what happens. As theta gets bigger, what happens to the overall time? We already see. As theta gets bigger, what happens to the overall time? It gets smaller, right? So if you want to make it, if you want to make the trip in as little time as possible, should you go straight there?
No.
No, the time goes, as theta gets bigger from 18 degrees, the time goes down. So what does E ask? Calculate the time if you walk 1,000 feet along the paved path and walk directly to the house.
Can you explain why it starts to go up right at the end?
Why it goes up? Well, it depends on the function. We'll talk about that logic in a second. It's not always going to be, because we'll logic that out at the end, okay? We're just getting some values. So is that good that it matches right there? Yeah. So E asks, calculate the time if you walk 1,000 feet along the paved path and then walk directly to the house. So in that case, what's your path look like? You go 1,000 feet from like this, and then you go directly to the house. So in order to find this, what do you need to find first? H, what did I call it? H, what did I call it? H, P and what? R? H, P and R, I think, right? And we know that this right here is 500, right? Well, this right here has to be 500. So what's that? You can use special right triangles. 500 what? Root 2. So what's the time going to be? 1,000 divided by plus 500 root 2 over 100. If we do that on our calculator, 1,000, 1,000 divided by 300 plus 500 second root 2 divided by what? 10.404. So what does that tell us here? So we figured out, we've done a few paths, right? What was the shortest time we came up with? The shortest time. So that's a little bit more than 10 minutes. So far it's 10 minutes. So we think it might be 10 minutes. It was 10 minutes when we did what? Do you remember?
Along the path and then go
Straight down and over. So when we went straight down and over, what was it? 10 minutes. When we went down and over, it was 10 minutes. When we went diagonally 45 degrees and over, it was only lost us like less than half a minute. But if we go all the way across on the sand, it takes us how long? 15 what? 15.811 minutes. So the question is for F, you're using graphing utility. For what angle is theta least? Why do we have to use a graphing utility? Because you guys haven't taken calculus yet. You don't know about rates of change, which you will shortly. What do we need to find? We want to find the lowest point. What does our calculator allow us to do? Let's find that minimum. Second calc minimum. So it asks for a left bound. So all you have to do is pick a point to the left of where you think the minimum is. And if I click too much, there's our left bound. Now I unfortunately have to click over to the right. If I click too much, this thing goes berserk, so I have to do it a little slowly. So look at the y values. Tell me when they start going up again. They start going up, right?
Yeah.
And don't please stop, please stop, please stop. Oh, darn it. Darn it. Enter. And then your guess should be a decent guess.
It doesn't matter.
No, it just needs to be, basically it needs to be between the 2 points.
Yeah, I mean, the
Enter.
graph, you put anywhere, it would be still.
Generally speaking, but it has to be between your left and right bound. It should be between your left and your right bound. You can run into issues where your calculator will get really angry at you. So what does it tell you the minimum is? This is cool. The minimum is, no, that's the minimum angle, right? So this means that when theta is 70.528785, time is 9.7140452 minutes. So what does this mean? If you want to minimize the amount of time, should you go over and then up? You should go almost all the way over and then up. Almost all the way over and then up. Now here's the thing. The reason is, now I'm going to answer your question now. The reason that happens, Jarrett, is because of this. Look at the situation here. The fastest travel time is on pavement by far, right? So you maybe want to get straight to the pavement, but by going straight to the pavement, you've traveled overall a longer distance. If you go straight there, it's overall a shorter distance, but the speed is a lot lower. So in this case, with these numbers, it comes out that when theta is about 70 degrees, so when you walk to about here maybe, right there, so you should walk all the way over, almost all the way there, and then do what? Then get on the sand. So to minimize this 9.7 minutes, you save, a quarter, like 15 seconds if you walk at a slight angle off of the house. And the reason for that is, yes, it would be faster on the pavement, but it's overall a longer trip if you go all the way over. That being said, if I change these numbers by a tiny, tiny bit, I can make it easily so that you definitely should go straight down and over. Yeah. If I change that 300 bit, if I change that 100 to like 50, if I made it really slow on sand, probably changes it one way. But if I make the pavement too much better, so if I change that 300 to like 350, it'll definitely make the most sense to go straight down. I'm just doing the math in my head a little bit. Right. Does that kind of make sense as to why that is? So it's overall, it's the best balance between distance and overall speed. Because the more time you spend on the sand, the slower you are. But the more directly you take to the pavement, the longer the distance you have to travel gets longer. Does that make sense? Yeah. Serious, there's many things in these questions that you take for granted that you can't, that you have to just realize they're there, but you have to realize they're there because you can't make up other stuff. Yes. So technically, could the person go past or not go to the house, or could the person go all the way around the world? Technically, sure. They could I could be like, hey, Denise, I'm going to shake your hand, but before that, I'm going to punch a hole through that wall, go down through the floor, go talk to Mr. Ryan, go outside, hire a blimp to send me to Germany, then the North. Like, you can go anywhere you want, theoretically, right? And then eventually I'll come around the world to talk to Denise here, right? You understand what I'm saying? Yep. Just keep it within realms of reality. Logically, you can think of this as, you don't have to explain it, just stay within the bounds. Logically, he's not going to go past the house. Think about it that way, okay? Logically, he's not going to go past the house. There's a lot of things we don't put in the student handbook that we don't specifically say you shouldn't do, but we know that you shouldn't do. Do you understand what I mean?
Common sense.
Common sense, yeah. We expect you to abide by common sense. We say it as, you need to be like a professional person. But there's for example, I think that's wonderful. Uh, 70 feet and 50 feet. Now, what are you trying to find? Yeah, we'll say that's A and that's B. You're trying to find the distance from A to B, right? You want AB. Can someone tell me what formula you need to use? Law of cosines, exactly, because you have side angle side. So you know that AB squared is equal to 50 squared plus 70 squared minus 2 times 50 times 70 cosine of 70 degrees. Anybody have an answer to 3 decimal places? Yeah, Bissell.
70.752.
Does that pass the reality check? Does that make realistic sense given this diagram? Yeah. Yeah.
Oh, yeah, I got it.
I mean, it's not an equilateral triangle, but it's decently in that realm, right? It's not that far off. Okay.
It's the law of cosine because
There's nothing else you can do. It's not a right triangle. You can't use the trig functions unless you make a right triangle some way, which you could do, but it'd be a lot harder. When can you use what? Law of cosines, side, angle, side.
If it's not marked, how do you know what's A, B, and C?
You just label it. I just called it A and B.
Oh, okay.
House 1, house 2,
Yep.
pony house, horsey house. I don't know. Anything you want. I generally, I mean, it would be good form for me to actually put those, label those points on your test so that when I'm grading them, I don't have to figure out what all the labels are. In general, if you have 2 points A and B, put them in alphabetical order if you're doing like from A to B, unless it absolutely matters which order. Okay, 26. How confident are you in an answer for 26? What do we think? Use hands here. 26. Pretty good? Those of you that are voting? No? 2? 2? Are you more confident about this one? How many triangles do we have? One triangle, right? And it says, what, 150 miles? And this is 100 miles. And this is 130 degrees. And this is, therefore, well, they tell you that that's 50 degrees. The other one's 130. Good. Okay, what's it asking? How far is it from Fort Myers to Orlando? An airplane flies from Fort Myers to Sarasota, a distance of 150 miles, and then turns through an angle of 50 miles and flies to Orlando, a distance of 100 miles. How far is it from Fort Myers? So that's, they want the straight distance. So again, they want from A to B. Does anybody have an answer using the law of cosines? What is it? Using to 3 decimal places? Someone new? Victor. 200 what? 560. How many people agree with that? Yeah. You use again the law of, and it says, through what angle should the pilot turn at Orlando to return to Fort Myers? So what is it asking you? So this is the plane's path, right? It's going like this, and then it's going like this. So it's heading in that direction. So to go back, so this right here is Orlando, and this right here is Fort Myers. What angle do you need to turn to? That's the angle they want right there. So to find that angle, let's call that, I don't know, point C. What angle do we want to find? Angle what? Well, we have C. A, B, C. Angle B is not specific enough. That could be 3 different angles. There are 3 angles at B. So that's the, we want A, B, C. We want the angle A, B, C. How do we go about doing that? Now we can, since we have, exactly, now we have 227.560. We know that sine of 130 over 227.560, what's that equal to? Sine of 227 over 560 is equal to the sine of angle ABC over what? Over what? 150, exactly. So sine of angle ABC is equal to 150 sine 130 over 227.560. So yeah, do that out. And did anybody, let's just, I'll pause. So end up with that angle, 30.328. So what's the, is that our final answer? No, we want 180 minus that, so it equals, and remember, on your calculator, when we did this out, so it's just 180 minus second ants, we get, bingo. So what angle does the plane need to turn? Yeah, I've always wondered about, you know, what's the if you actually had the real path of an airplane, because does an airplane go like this and just turn immediately? No, it's an arced path, right? I mean, imagine the true path of an airplane when you're looking at it from above. What it ends up doing is this: it's traveling along, and then it makes a gradual turn like this. So how does it calculate the angle? Well, this is its original flight path, right? And here's its new flight path. So what angle do they measure? That would be the angle they measure, right? You're turning until you make it. You know, it's all done by, you know, my knowledge of plane navigation is poor, but I'd imagine it's something to do with north, south, east, west, directional navigation. Yeah, probably. And also, what makes it more fun when you're flying a plane? Are you on a flat surface? No, you're flying on a. The Earth is the shape of a sphere. You're flying on a sphere. You're not flying on a flat surface. So the projections of flight plans are really interesting. When we flew, so here's the west coast right here, and here's Southeast Asia, and Russia's up here, and Korea. Our flight path, when we went to Cambodia, we flew from Los Angeles. Literally, the flight path looked like this. It looked like that. Was it actually a bent line like that? Not really. Not really. Because it was following the curvature of the Earth in a direct fashion, going slightly more north to hug coastlines. It's pretty cool. Anyway, I find it neat anyway because it's surprising because we look at the Earth. We look at the Earth like the world map. Over there, we look at it as a flat projection. It's not the case. Is Greenland really that big? No, Greenland's not that big. Is Russia really that tall? No, Russia's when you look at the boxes for latitude, longitude, it's a lot flatter than it appears to be. Okay.